answers for assignment 7. So in assignment 7, there are 4 different questions I had to answer. I'll go each of the questions one by one. So the first question was a hash table that hashes all values to the same slot is essentially equivalent to what other data structure? A hash table that hashes all values to the same slot is essentially equivalent to an array or list-based data structure. In this scenario, all the elements are placed in the same slot and hash table effectively becomes a linear list. As a result, the performance of operations on such a hash table would be similar to that of the operating system on a regular array or list with an O of n time complexity for searching and insertion and deletion and operations. It could be also be similar to a dictionary data structure using key and value. For example, hash table ADT is a data structure where the position within the data structure isn't explicitly determined by an integer, and each position and element is stored is known as a slot or bucket. The storage of information can be thought of as key and value pairs. Insertion is done via put action and accession is done via get action. And this kind of similarly mirrors the dictionary data structure. The second question was analyze the hashing functions that were discussed in the lecture slides. Elaborate on the benefits and drawbacks of each functions. Hashing functions in a hash table are crucial for distributing data evenly across the available slots to minimize collisions and improve performance. And let's analyze some common hashing functions that was discussed during the lecture slides. So the first function that was discussed was the lose-lose function. This is a simple hashing function where the hash value is calculated by summing the ASCII values of each character in the key. The primary benefit of this function is its simplicity and ease of implementation. However, the drawback is that the simplicity also leads to poor distribution of hash values, resulting in a higher likelihood of collisions. The summing approach tends to group keys with similar characters together, leading to clustering and reduced performance in hash table operations. The second function is rs hash function. This hash function is a simple and efficient hash function that uses a combination of bitwise operators and shifts to calculate the hash values. The function works by iteratively multiplying the hash value by a prime number and adding the ASCII value of the next character in the key. The final hash value is then obtained by performing bitwise operations. The benefits of ours hash include good distribution and relatively low clustering, leading to fewer collisions compared to the lose-lose hash function. However, the drawback is that it may not be as strong as some other hash functions in terms of avoiding deliberate collisions or minimizing hash function in certain edge cases. The third function is DJB2 hash function. This is a popular and widely used hash function created by the Daniel J. Bernstein, and it uses bitwise operations and multiplication to calculate the hash value of the key. The function processes each character of the key one by one, updating the hash value. DJB2 has better distribution properties compared to both lose-lose and RS hash functions, resulting in reduced cluster and few collisions. It is generally faster and provides good distribution for a wide range of input data. However, it might be not as strong as against certain attacks targeting deliberate collisions. The next hash function is SDBM hash function. This is another example simple hash function that uses bitwise operation shifts in addition to calculate the hash value. It processes each character of the key and updates the hash value accordingly. SDBM provides decent distribution and performs well in practice for many applications. It can help reduce clustering and collisions compared to lose-lose hash function, but it may not be as robust as more advanced hash functions against certain types of inputs or attacks. The next we look at is hash table ADT. Hash table data abstract data type. Hash table ADT is not specifically for hash function, but rather a data structure that incorporates a hashing function for key value storage and retrieval. The benefits of using the hash table ADT are its efficient average case performance for insertion, retrieval, and deletion operations when hashing function is well distributed and collision resolution is effective. It provides fast access times and is widely used in various applications for its simplicity and performance advantages. However, the choice of hashing function and collision resolution method greatly influences the overall performance and security of the hash table ADT. In conclusion, each hashing function discussed has its strengths and weaknesses. Simpler function like lose-lose may be easy to implement but suffer from poor distribution and high clustering, leading to more collisions. On the other hand, Functions like DJB2 and SDBM offer better distribution and reduced clustering, resulting in fewer collision and better average case performance. However, the trade-off lies in the computational complexity and potential vulnerability to certain attacks. Choosing the right hashing function depends on the specific requirements and use cases of the application. For critical and security sensitive systems, more sophisticated hashing functions, or even such as cryptographic hash functions, should be considered to ensure robustness against potential attacks. It is essential to elaborate the specific characteristics of the data and potential threats to make an informed decision on the most suitable hashing function for a given scenario. The third question that was asked in the homework was analyze two methods for resolving collisions in hash tables that were discussed in the lecture slides. Elaborate on the benefits and drawbacks of each method. So let's take a look at the first method that was described, the open addressing method. Open addressing aims to find an alternative slot within the same table for the colliding element. Linear probing, quadratic probing, and double hashing are common open addressing techniques. Open addressing saves memory as it does not require linked lists, leading to a better cache performance and reduced memory overhead. However, it is more susceptible to clustering, which can lead to further collisions and degrade performance. So what could happen when we're doing linear probing? So during a linear probing, information could cluster, and common hashes lead to increasing long put get times. However, the benefit to hashing is relative speed with the goal of big O of 1 performance. And what could happen in the most extreme cases? Constant hashing to the same location, incremental indexes leads to clustering of all data. Put or get actions take big O of n. And let's take a look at the second method, which is chaining. Chaining involves using linked lists or other dynamic data structures to store multiple elements that hash to the same slot. When a collision occurs and the new element is simply appended to the list in that slot, chaining handles collisions effectively and allows for flexible use of memory. However, the drawback is that it requires additional memory for the linked list, and cache locality might be affected, leading to slightly slower access times. And any number of elements can be stored at a given hash value, but we can run into the same problem as we did with open addressing, as discussed previously. If we always hash to the same value, we have performance issues approaching big O of n as the list grows. The last question that was asked was, what strategies and issues should you consider when you're resizing a hash table? What are likely complications? How would you address? So I have listed some strategy and some issues and how to resolve those issues. So let's go over the load factor. The load factor is the ratio of the number of elements to the number of slots in the table. When the load factor exceeds a certain threshold, commonly 0.7 or 0.8, it's time to resize the hash table to maintain efficiency. Resizing the table involves creating a new larger table and reshaping all the elements into a new table. The next one is resizing strategy. When resizing, it is essential to choose an appropriate strategy. Common strategies include doubling the size of the table, adding a fixed number of slots, or using a more complex formula to determine the new size. Doubling the size is a popular strategy as it provides a good trade-off between the complexity and memory overhead. Some of the issues and resolving these issues include reshaping. So during sizing, all elements need to be reshaped and distributed into a new table. This process can be computationally expensive and may cause temporary performance drops. One way to mitigate this issue is by performing the reshaping incrementally over multiple operations. And the next method is the concurrent access. When resizing a hash table in concurrent environment, for example, multiple threads or processes accessing the table simultaneously, careful synchronization is required to avoid data corruption or loss. The next case we are looking at is memory management. Resizing a hash table involves allocating new memory for the larger table and deallocating the old memory. Proper memory management is essential to avoid memory leaks and ensure efficient memory usage. To address these complications, it's crucial to carefully design and implement the resizing process. Additionally, choosing appropriate hashing functions and collision resolution methods can greatly impact the overall performance of the hash table. Regular monitoring of the load factor and performing proactive resizing when needed can help maintain the efficiency of the hash table operations.